Welcome to the debate.
Today, we're diving into a really fundamental conflict in software design. It's all about how we handle errors.
That's right. We're looking at the classic battle between traditional exceptions versus these newer type system-based ways of doing things, like Rust's result or what C++ is doing now with std expected.
And the core question, really, is has the industry's shift towards these explicit value-based models made old-school exceptions, well, inefficient, maybe even obsolete?
Or do exceptions still hold a vital place? Are they maybe the necessary default for handling truly catastrophic failures, those really unexpected problems?
So for today, I'll be arguing that exceptions offer an essential structural robustness. They give clarity, especially for those big, anomalous failures. It helps keep the main logic clean.
When I'll be taking the position that these modern, value-based systems, they offer much better explicitness and, crucially, predictable performance. They fix the big problems, like hidden control flow, that exceptions have always kind of struggled with. Okay, so my stance really comes down to clarity and safety built into the structure. The big philosophical win for exceptions, I think, is how cleanly they separate the main logic, the happy path, and the try block from all the error handling stuff. It really helps manage complexity, It stops the main algorithm getting buried under endless if error checks. That's how you end up with, spaghetti code, frankly.
Right.
But maybe even more critical is this idea of, let's call it the principle of unignorability. If an error happens and you don't handle it, what happens? The program stops, fail fast. And that's almost always the safer default. It's not like error codes where, a programmer could just forget to check it and the application carries on potentially in a completely broken state. An unhandled exception forces you to deal with the problem, or at least it stops things before they get worse.
Okay, I agree safety is absolutely key, but I think getting that safety through implicit mechanisms like exceptions comes at a really steep price. The biggest conceptual problem with traditional exceptions for me is the hidden, non-local control flow.
Yeah. When a function throws an exception deep down in a call stack, it's not just returning. It's basically acting like a hidden go-to, potentially jumping over many, many levels of functions. And that just makes code incredibly hard to reason about. You can't just read a function and know what it does. You have to consider this invisible path that could whisk control away at any moment. It violates that whole principle of least astonishment.
Well, I think calling it a hidden go-to is maybe a bit of an oversimplification of stack unwinding's utility. Yes, it's a non-local jump, but it's a controlled one. And that's where the safety really shines, particularly in languages like C++. I'm thinking specifically about how exceptions work with RAII, resource acquisition is initialization.
Right, RII.
Yeah, for anyone listening, RAII basically means when you create an object and it grabs a resource, memory, a lock, a file, whatever that resource gets automatically cleaned up when the object goes out of scope or is destroyed. And the crucial part is the exception mechanism guarantees destructors get called even if an exception cuts the execution short. This is absolutely vital for preventing leaks. It's an automated safety net that error codes just can't provide without tons of careful manual and honestly error-prone cleanup code everywhere.
Okay, the RA guarantee is powerful, I'll grant you that. But the performance side of exceptions? It's just devastating when you're not on the happy path. People talk about exceptions being zero cost in normal operation, but the instant you actually throw one, the cost skyrockets. You're talking about complex runtime operations, walking the stack, finding the right handler, runtime type checks. It can be literally hundreds, even thousands of times slower than just returning a value. That kind of unpredictable timing makes exceptions completely unsuitable for performance-critical code or embedded systems. And frankly, it makes them unsuitable for handling errors that aren't really exceptional at all, just, expected possible failures.
But isn't that the point? For exceptional circumstances?
Well, yes, but the industry trend shows we're finding better ways to get both safety and explicitness without that performance cliff. and without the confusing control flow. Look at the Convergence, Go with its error return values, Rust with result, and now even C++, the historical bastion of exceptions, adding std.expected in C++23. It's pretty clear evidence, isn't it? These newer systems put the possibility of failure right into the function's type signature. It holds either the success value or an error. So you get the explicitness of error codes, but the safety, the unignorability, comes from the compiler forcing you to handle it. It sort of solves the main problems of both older approaches at the same time.
Okay, let's dig into that trade-off. Implicit safety versus explicit flow. Because I agree that's really the core of it. You're saying compiler enforcement is better for safety. But I'd argue that the automatic, implicit propagation of an exception up the stack is actually a feature, especially in big, complex systems with many layers or components. It reduces the cognitive load on developers working in the middle layers.
I see the appeal of reducing cognitive load, sure, but the modern approaches like Rust's result T, E, they handle this pretty elegantly without losing explicitness. The function signature tells you flat out, this might return an error of type E. Then the compiler makes sure you deal with that error possibility before you can touch the success value T. So it's explicit, it's safe because the compiler checks it, and you avoid the heavy runtime cost and the confusing non-local jump of traditional exceptions. It keeps the reasoning local.
I'm not sure the locality is fully preserved in very large applications, though. And while I get the compiler guarantee point, even with modern approaches, robustness often relies on programmers following specific conventions. Like in C++ with RAII, the whole system falls apart if a destructor throws an exception, right? Program terminates immediately. So there's discipline required there, too.
True. Destructors shouldn't throw. That's a core C++ idiom. Exactly. And while result is safer locally, for really deep call stacks, that automatic silent climb of an exception just feels more composable sometimes. The burden of propagating the error still exists in these explicit models, whether it's Go's endless if error not nil blocks, or even Rust's question mark operator, which is nice syntax, I admit. You're still manually forwarding that error value up the chain. It clutters function signatures and forces every intermediate layer to be aware of and participate in the error handling mechanism.
But the question mark operator in Rust is really quite effective at cutting down that boilerplate while keeping the explicitness. You see exactly where propagation might happen, and importantly, it's a zero-cost operation when it does propagate. My point is, an explicit operator is far better than an implicit, hidden runtime jump that needs the whole runtime system to unwind the stack and do all sorts of expensive bookkeeping. Okay, let's maybe look at it from a different angle. Context-specific domains. Where does each approach really shine? For instance, the source material points out that exceptions are often the only clean way to signal failure from a constructor. Since constructors don't return values, throwing is the standard mechanism.
That's a fair point about constructors.
And exceptions seem ideal for genuinely catastrophic runtime problems, things like running out of memory or maybe a fundamental OS kernel failure. In those cases, the high cost of throwing is perfectly acceptable because it should be incredibly rare. And for all the normal execution time, you've benefited from the cleaner code and potentially better performance on the happy path because you're not littering it with error checks.
I'm sorry, but I just don't buy that the rare event argument really holds up across the board, especially when you consider high reliability systems or embedded systems. These areas completely contradict the idea that exceptions are universally robust.
How so?
Well, in those fields, exceptions are often just turned off, disabled entirely at the compiler level. They're seen as fundamentally incompatible with systems that need predictable timing and have tight resource constraints. Why? Because the non-deterministic time it takes to unwind the stack, plus the memory overhead needed for the unwind tables themselves, it just clashes directly with those core requirements. When safety is paramount or timing is critical, the predictable low-overhead error code, or now the value-based approach, is the mandated standard. That proves exceptions aren't the answer everywhere.
I think that shows context matters, absolutely. But it doesn't mean the mechanism itself is flawed. The constraints on a tiny microcontroller are just vastly different from, say, a large web server application, where your priorities might be more about maintainability, rapid development, and clarity, rather than microsecond-level timing. For that kind of application-level logic, where failures are genuinely unexpected, exceptions can still be the cleaner choice for composing the code.
And yet, even in C++, the language that arguably defined modern exception handling, the arrival of std.expected in C++23 feels like a huge institutional nod towards the limitations of the pure exception model, even for general code.
A nod maybe, but not a replacement.
Well, the standard library is now officially sanctioning a performant, type-safe alternative specifically for predictable, recoverable errors. That seems like a pretty strong signal that the future is at least hybrid. It suggests the explicit, value-based way is becoming the preferred approach for almost everything that isn't a complete system meltdown.
Okay, I agree it's a major shift, and st.expected is important. But I don't think it eliminates the need for exceptions. It really just formalizes fixing an anti-pattern, which was using exceptions for everyday predictable things like file not found, where they were never really appropriate. Exceptions, I'd argue, remain the best tool when the error source is far removed from the handler, especially across architectural boundaries.
Explain that boundary idea more.
Think about a web server. If some low-level network function fails deep inside the stack, do you really want every single function between that point and the top-level request handler to have code specifically to check, wrap, and forward that error value?
Ideally, yes, the type system would track it.
Perhaps, but it's often cleaner to let the exception automatically unwind the stack, cleaning up resources via RAII along the way, until it hits that architectural boundary like the main API request handler. And there, you put an explicit catch block. That's where you translate the internal failure into something meaningful for the outside world, like sending back an HTTP 500 error. The unwinding handles the cleanup automatically across layers.
But isn't the risk there catching overly broad exceptions, like catch or catch std exception, and that can hide the real problem and make debugging harder? The explicit type approach forces you to be rigorous about what failures are possible and how they're handled or translated. The translation at the boundary becomes part of the explicit contract, not something triggered by an implicit runtime halt.
I see the danger of overly broad catches, but disciplined use avoids that. My point is the guaranteed cleanup during the automatic unwind to that boundary is incredibly valuable. It keeps the intermediate logic focused on its job, not on error plumbing, while still ensuring safety. They're complementary tools, really. Value types for local, expected issues, exceptions for long-distance, catastrophic failures.
Complementary, perhaps? But I still see the trend favoring explicitness.
So, to wrap up my view, the core strengths of exceptions, that guaranteed resource cleanup with RAII during stack unwind and enforcing the fail fast principle for unhandled errors, those remain incredibly valuable, particularly for truly unexpected system-level failures, especially when code clarity on the happy path is a high priority. Modern systems are great for common errors, absolutely, but exceptions provide that automated safety net for the really serious, unforeseen problems.
And my summary is that error handling is clearly evolving towards compiler-checked safety and predictable performance. By making failure an explicit part of the type system, like the result pattern, and by getting rid of that costly, non-deterministic throwing mechanism, these value-based models offer, I think, superior robustness and predictability across more domains. The modern approach feels like a more elegant solution, taking the best parts of the older methods without their biggest drawbacks.
It certainly seems the overall direction is towards leveraging the compiler and the type system more, taking some of that burden of ensuring correctness off the individual programmer.
Right. And ultimately, the best way isn't universal. It's an engineering decision, a trade-off based on context. Are you optimizing for the happy path's clarity or for performance determinism and complete explicitness? The good news is the toolkit we have now is more flexible and type-safe, helping us build robust software that can handle both its expected paths and its many inevitable unhappy ones.